And with that, we'll go ahead and kick off into our first talk, who's going to be from Matt Gonzalez. And Matt is an independent audio developer with more than 20 years of experience. And Matt also helped to implement the Direct2D uh, graphics for Juice 8. And today he's going to be speaking about the past, present, and future of Juice graphics. So over to you, Matt.
Thank you, Josh. Hi, everybody. Greetings from Southern California. Good afternoon, good evening, and good morning, wherever you are. Josh, could we start by asking how many people have experience with Juice? People in the audience, what's their level of familiarity? This is kind of targeted towards that, and so it might help to know that. But I'll proceed anyhow while you do that. Let's see. So let's get my screen share going here. So yeah, like Josh said, I'm Matt Gonzalez, and I've been doing this for an embarrassing length of time. I've been doing this really since I was about 14. My dad bought me a Texas Instruments 99 4A with 8K of RAM, and I was pretty excited to get it at the time, and it's really been kind of nonstop ever since. So screen share, there we go. Okay, yeah, so that's me, that's my face. Like I said, I've been writing software since about 1981. I've worked for Echo Digital Audio on and off since 1993. So you can do the math on that. I'm not going to. And I've done a lot of consulting work on the side. At times have been lean, good for the company. I've done pretty extensive work in the pro audio field. If you're old enough, you probably remember the Layla audio interfaces from the late 90s. That was one of the first multi-channel interfaces for a PC. It had a PCI card. I've worked on FireWire, USB. I've worked on plugins. If you can see behind me, there's some red guitars. I don't have my camera on right now, but you can see that. And those are some prototype self-tuning guitars that we did with Gibson about 15 years ago, if anyone remembers the robot guitar. And I've been a Juice fan for about as long as there's been Juice. I think since version 1.5 or something like that. If you look at my forum membership, I've been a forum member since 2005, so I'm a big fan of Juice. And which kind of brings us to what we're going to talk about today, which is the story of a hobby that just spiraled wildly out of control. I didn't plan to be in this position. The thing that's kind of strange about where I'm at right now, as I was at ADC about a month ago in Bristol, and at the Audio Developer Conference, and I'm walking around, and everyone's asking me about graphics, and I've worked in audio for 30 years, but over there I'm the graphics guy, which is a relatively new development. So it's kind of a fun position to be in, and it's odd to be on the Audio Programmer podcast. This isn't a podcast, right? With the Audio Programmer meetup and talking about graphics. But here we are. As a Juice fan for a long time, as a Juice user, as a developer who's wanted to build cross-platform audio APIs and UIs and, not APIs, UIs and plugins and things like that, what I really like, I want to be able to build this kind of crazy UI that you see in movies. Like, you see there's all like that's from a James Bond film, right? And I want to have that run full screen. I want to run at the monitor refresh rate, and I want to build it using Juice, and I want it to be cross-platform. So I want all that stuff. I want, this kind of crazy UI here. This is a bunch of nonsense, right? There's a hexaflexagon process that's running at level 2. There's all these crazy glyphs, these graphs all move around and they animate, and they're great. But I want to build something that looks like this, but really works and is actually useful. That's from The Expanse. That looks like you could pilot it, right, without even trying. That's from the Total Recall remake. But, some graphic designer went to a lot of trouble. So I look at that and I think, why can't I build that using my Juice app? And historically, Juice has, graphics hasn't been Juice's strong point. I guess I'll put it that way. And I say that with love, and I say that as a fan. And that's the joke I like to say is that Juice is the strength of Juice is that it's cross-platform. If you're not familiar with Juice, Juice is a C++ library that lets you build plugins and apps using C++, but you can write it in a cross-platform manner so that 99% of your code is platform independent. And so the strength of Juice is that it's cross-platform, and that works really well. And the strength of Juice is working with audio. It's got all those great DSP routines built in, audio device handling, stuff like that. But the downside of Juice, I think, is that it's cross-platform. And as far as graphics go, it's really good at audio. So that's been a complaint for a long time from users, is the graphics performance, the UI performance. They've done multiple surveys of their users. And that's the number one request for the last 10 years has been, how do we do better on the GUI performance? And there's been multiple threads on the forum talking about it and that kind of thing. I think it's because most users up until recently have been using the JUCE software renderer. And so the JUCE software renderer is part of the JUCE graphics stack. You can see there, there's the JUCE graphics class. If you've used JUCE at all, you're familiar with that. From your paint handler, that's what you're using to fill rectangles, set clipping regions, set the brush color, stuff like that. That's going to an implementation of the low-level graphics context class. In this case, it's the software renderer implementing, deriving from low-level graphics context. The task of the software renderer is to fill a bitmap, to rasterize a bitmap in CPU memory, which is then passed to the screen using some platform-dependent API. In this case, it's the Graphics Device Interchange API on Windows. But of course, on Mac or Linux or iPhone, it would be different depending on the platform. What we really want, what everyone's been asking for a long time, is cross-platform GPU-based rendering. The graphics layer would still be the same, but now we would have some platform-specific low-level graphics context implementation, which would generate a command list and pass that command list to the GPU, so the GPU rasterizes the texture in the GPU rather than doing it on the CPU, thereby freeing up CPU time and probably getting better quality too out of your rendering. That's turned out to be surprisingly hard to do. GPUs are, like it says, they're mainly meant for 3D rendering, and there's some very specific, difficult problems that you want to do in 2D graphics, like stroking paths, like that Bezier spline on the right of the slide there, drawing text, doing very small details. It turns out GPUs suffer. They do everything in groups of 4 pixels, and if you just want to draw something that's less than 1 pixel, the triangle efficiency goes way down. And doing 2D clipping is actually surprisingly difficult on the GPU, especially if you have a complex clipping region. So it's a sense of, GPUs are essentially designed for video games. And so getting 2D graphics to work on you'd think it'd be easier, you'd think it'd be one less, but it's not. And so to dig into that a little more, say you want to go ahead and stroke a path like you've got. That's just a standard JUCE API call, graphics stroke path with this path and with this type of stroke. Something has to happen. And then we end up feeding the 3D rendering pipeline. In that case, it's Direct 3D 11, but they all pretty much work the same way. But that's a fairly complex pipeline. There's a lot going on there. So what has to happen in that middle stage is we need to do a couple of things. And this is, again, from the point of view of, this is about 10 years ago out of date. This is not the way you do it now, but this is the way Direct 2D does it. So that's just a little print. I'm sort of time traveling from the year 2014 in this context. But essentially what we have to do is for that path, we have to generate a polygon mesh, just a set of vertices and triangles all interconnected. We have to then draw stuff on that polygon mesh using shaders and textures, and then we have to manage the resources necessary to keep that pipeline flowing. If you spend any time browsing through the JUCE code base, like I have, you'll realize JUCE has had a Direct2D renderer in the code base since 2010 that doesn't work. That's the first commit message I could find. I decided a couple years ago I was going to try and fix it. I was bored. It was COVID. I was locked down. And but I found it wouldn't even build. I started rewriting it about 3 years ago now, I guess. Maybe 4. Yeah, almost 4 years ago. And eventually got it together. That's, I think, more time than I want to spend on it right now. I'd be happy to talk more about that whole process and getting it together, getting it with the JUCE team, working with them. Eventually it made its way into JUCE 8, but that's another story. But instead, I thought I'd focus today on the technical details of Direct2D, how it works, its limitations. As a developer, how do you interact with it? How can you work with it? And where things might go from here. So I'm going to focus on that. Direct2D essentially works. We wait for a vertical blank notification to come in. We wake up the renderer. We tell Direct2D, begin drawing. Direct2D initializes its internal command batch because its job of the renderer is to build up a list of commands while you're painting and then pass those off to the GPU. We go to the paint handler. In the paint handler, this is where your app is going to run, your plugin, your graphics callback is going to happen. In there, you're going to fill rectangles. You're going to draw circles. You're going to set the color to cyan. You're going to set the clipping region. Eventually, you're done drawing. We call endDraw. endDraw takes that whole command queue, passes it to the GPU. The GPU rasterizes a texture internally. We present that bitmap to the screen, and the cycle continues. Digging into that a little bit more, say again, you want to go ahead and stroke this path. We want it to look like it does on the right, and we want it to be nice. We want it to have nice rounded corners. We want it to have clear contrast, like sharp edges between the blue and the orange there. We want it to look like it's been plotted with a plotter pen tracing a path through space. But for this stuff, the GPU only knows how to make things out of triangles. So what we have to do is we have to take that path and we have to convert it internally to a direct 2D geometry. That happens on the CPU. That's an internal pass. Direct 2D, then it has to, we take that geometry, we have to transform it to fill the space, whatever, you'll pass it an affine transform, it'll fill the space, rotate it, stretch it, skew it, whatever. We then have to tessellate that geometry, which is turning it into vertices and triangles. And then we have to pass that to the command queue, put it in the command queue to go to the GPU to be transformed, to be rasterized. Tessellation is an old idea. It's the process of fitting shapes together in a pattern with no spaces in between. That is a mosaic, a picture I found of a mosaic in Marrakesh. You can see it's just filled with that regular geometric pattern. So tessellation is an old idea that obviously predates computer graphics. In our case, the GPU needs stuff turned into triangles. It just wants to deal with meshes of triangles. So in this case, that tessellated path turns into a shape like this. And you can see all those little triangles in there. This is a mode you can put the renderer in where it gives you back the triangles rather than painting the path directly. So how are we doing, Joshua? Is that all coming through okay?
Yep, everything's looking great.
Okay, great. Good. So let's switch over for a second here and talk about why bother. Why go? I've talked to a lot of users over the last couple of years, a lot of people, a lot of developers, all of whom have come up with their own homebrew. They use the SDL, they use BGFX, they're writing their own OpenGL shaders. They've all come up with their own ways to get more performance out of JUCE. They've all come up with their own, everybody's got their own homegrown approach to it. And or some people think the renderer is fine as it is. We don't need to improve things. There's a lot of opinions, there's a lot of perspectives. Personally, for me, like I said, what I want is I want more performance and I want things to, and so what's the point of all this? Is it really faster? And so let's take a look at the JUCE demo. If you've used JUCE at all, then you're familiar with the JUCE demo application. Okay, so this is the, on the left here we have the software renderer, and on the right we've got the Direct2D renderer. This is the JUCE demo, and I'm going to go ahead and play that. So this is just a video clip, but if running it live, this works this way. And you can see on the left, the software renderer is running at about 5 milliseconds, and we're getting a good frame rate. We're getting about 60 FPS on the left, but on the right, you can see there it's about 10 times faster. The actual paint handler time, it's 50 milliseconds instead of 6. That's already pretty good. The software renderer is doing well in this situation, but already we're 10x faster. And if you look at the effective frame rate, you can see the big difference there. When things start to get interesting is when we use this tiled image test. And this is where you tell JUCE, take this image and use it as a brush, fill the whole space with this image. And I'm being unkind to the software renderer here. You can see I've got the high quality image interpolation turned on. I'm rotating the image, so the software renderer is having to do all that math to move that image through space. And you can see it's struggling a bit. It's down to about 50 milliseconds a frame. We're getting 16 frames a second. On the right, Direct2D is taking 30 microseconds to render that frame, to execute that command. And it's not even breathing hard. The GPU is not breathing hard. That image is already stored in VRAM. So it's just issuing a single command to the GPU. And so the performance difference in this case, that's when I started to get kind of excited when I saw these kind of performance differences. One thing that would be, I think it might be of interest to, this is a thing that hasn't really been talked about publicly, is that the JUCE renderer has some pretty extensive metrics built in internally. And if you just set this build flag, if you just set JUCE Direct2D metrics in your app, you can use this here. And if you see here, this is going to find an app. This is a separate app just called the Direct2D metrics app. So on the left, we've got the JUCE demo. On the right, this is the metrics app. And I've got the JUCE demo built with Direct2D metrics enabled. And the metrics app has gone out and what that actually is doing is it's creating a named pipe. There's a server now inside the JUCE app that can report metrics. So you only want to turn this on while you're developing. Obviously, you don't want that in your app running there all the time. But you can see here now that I'm reporting all of this internal stuff that's going on with all these activities. So this is really helpful for profiling. If you're drawing and you're getting slow performance with your graphics, you can build your app with the metrics turned on, And you can run this metrics app on the right, and from that you can get a real sense of what's happening inside your frame. Like you can see here that, I'm spending a fair amount of time creating geometries, creating these paths. And this app is going to be available as part of a new module that I'm putting out. I'll be talking about that in a second. So let's talk about some of the challenges that we've faced with Direct2D. To me, Direct2D has represented a fairly significant paradigm shift for the community and for me and for the JUCE team, really for everyone. Largely because I think we've been used to living with the existing renderer for a long time. We're used to, it's sort of, I think everyone's been sort of living inside the box, created, conceptually created by the software renderer. We've been used to that for a while. People are used to working around it. This is sort of how JUCE apps work. And there's kind of a mental shift now because this renderer just works fundamentally differently because all the drawing happens on a different device with a different memory space. We put a lot of effort into backwards compatibility, and we did the best we could, but there were some things that didn't come up during beta, and that's been some of the challenges we've run into. And some of this, I think, was due to limitations in the JUCE object model, where it wasn't necessarily intended for this purpose. And I'm going to diverge for a second. I'm going to talk about the circle ellipse problem, which if there's any C++ developers, you've probably heard of this already if you spent any time reading the C++ FAQ, but I'm going to just review that briefly. So the circle ellipse problem is a classic problem in object-oriented design, and I want to disambiguate a little here because I'm not talking about graphics anymore. I'm not talking about actually painting circles or ellipses on the screen. I'm talking about abstract geometric concepts. I'm talking about the actual idea of a circle versus an ellipse. And the circle ellipse problem has to do with how you take a real world idea, like a circle or an ellipse, and how that maps, how you convert that to an object-oriented hierarchy. And the question is a circle a kind of ellipse? Can you declare a class called an ellipse? An ellipse would have, say, a center position, and it would have an X radius and a Y radius, right? Because an ellipse can be a different width and it's a different height. Can you then say, well, a circle is a special kind of ellipse? Can I have a class called circle derived from ellipse? And if you search for this problem, there's all kinds of people arguing about it in Stack Overflow and places like that. If you read the C++ FAQ, which I agree with, the circle cannot be derived from ellipse because an ellipse can do something that a circle can't do. In other words, the circle can't honor the contract promised by an ellipse. Specifically, if you try to set an X and Y radius for like say the ellipse class has a set size call to set the X radius and the Y radius, the circle can't obey that. The circle can't, because a circle, of course, has to have the same X radius as a Y radius. And again, this is the kind of thing, if you read the C++ FAQ, it's really pretty funny because people argue about this all the time. But again, this is how I see it. This is what I agree with. And I think there are two solutions that I know of, which is you make them unrelated classes. So maybe circle and ellipse have similar functions, but they're not derived from each other, or you have them derived from some common base. Whatever minimum common functionality they have is in that base class, rounded shape or whatever. But then the circle and ellipse have different methods going down. And I think in this particular case, what we ran into the circle ellipse problem with the JUCE image class. The JUCE image class, the contract with users, it has a few underlying assumptions that people are used to, which is that they can readily access the bitmap data because the bitmap data is just an array of pixel values in the CPU. The bitmap data can be any size because it's just, again, an array just in your CPU RAM. And the bitmap data will persist. It won't just vanish. However, with Direct2D, the performance benefits of storing the image data in VRAM, in the GPU, are enormous. We saw that earlier with the demo. But it violates all those rules. Now the bitmap data is not readily accessible. It's in a different memory space on a different device. You can map the data from the GPU back to the CPU, but that's expensive. It takes several milliseconds, and that really starts to add up in your paint handler. Bitmap sizes are limited to the maximum texture size of the GPU, and that's device specific. And then finally, bitmap data may vanish. GPUs can go away. In one case, imagine you have an external GPU hooked up to your MacBook with a Thunderbolt cable, and that cable gets pulled out. That data is gone. On Windows, if you change the DPI setting for your desktop, the adapter resets. So any data you have in VRAM is gone. And so I think what I've concluded, so there's been some traffic on the forum recently, people talking about this stuff they've run into, and I think fundamentally what I've concluded is it's because it breaks the object model. We've run into the circle ellipse problem. So I think the solutions are to either come up with a new class, like a transient image class, which would be a separate class with a similar API to image, or extend the image to allow GPU storage. And if you're a JUCE user and you've been concerned about this, this is in process right now, and I think it'll be resolved soon. I'd be happy to talk about that more. So that's been one of the challenges we ran into, is that the existing class model didn't map necessarily. And I don't think this is a direct 2D specific question. I think this is a problem that would have happened with any hardware accelerated, any GPU accelerated solution. We would have run into this. Josh, I'd like to stop and take questions now at this point.
Okay, great. So if anybody has any questions, please feel free to put them through to the chat. One question that I had was, what is the Mac equivalent of Direct2D?
Metal. Well, actually, no, actually, I'm sorry. Mac doesn't necessarily have a direct equivalent to Direct2D, in my view. Direct2D is really a software library that sits on top of Direct3D, that sits there and does all the thing that if you saw that one step with the big orange arrow in the middle, it's basically that. And the Mac has a few layers. It's got core animation. Core graphics, I think, is now actually pretty good. Core graphics used to not be GPU accelerated, but the JUCE core graphics renderer is pretty fast. I don't know if there is a strict equivalent that maps quite. The Direct2D mapped almost directly one-to-one to the JUCE low-level graphics context, and I think core graphics does pretty close to that. And I would have said that that wasn't accelerated before, but I tried it recently and it was really fast. I don't think there is an equivalent on Linux. There's core animation, which does some of the things, that does some of the layering. Like a core animation will let you build layers and it'll let you draw a path in the layer and say, I want to clip to that layer. So my sense is there's different bits of it in different Mac layers. And so I think core graphics is probably the closest you get right now. But I'm not sure there is a. Yeah, I actually. Well, you're stealing my thunder a little bit, so I'm gonna answer that question more at the end of the talk, if that's okay.
Okay. Another question that I wanted to ask is, working with a legacy API that's been going for so long, has there been any discussion to, okay, what if we just revamp the entire?
Yeah, I think that's been an ongoing conversation. I think that's been an ongoing conversation for a long time. So my position is a little weird, right? Which is that I'm not a member of the JUCE team, right? I float around the periphery of the JUCE team. I know those guys, I consider them to be friends, but I'm not an official JUCE team member, and I want to be really clear about that. So my opinions are just my own. I'm really just a JUCE customer ultimately. I just ended up the planets aligned and there was a harmonic convergence. So the work I was doing as a hobby ended up being something that worked out well for JUCE 8. But I'm not any type of official. I think they've talked about that a lot. I think I guess what I'll say is ultimately I've noticed there's no shortage of opinions. That continues to be a rich natural resource that's widely available. And you'll talk to a lot of developers that say, like the guys who are talking after me, like you guys are doing WebView stuff, right? You're doing, and that's great. And there's a lot of programmers that want to do WebView, right? They want to design their plugin in Figma, and they want to use Electron or something like that to do their UI, bag the whole JUCE component framework, great. And they think that's a great idea. And there's a whole other group of people say that's a terrible idea. You should never do that. You'll get, and I don't know if there's a lot of consensus. I think what I have learned is that it's really tough to shift away from the legacy stuff at this point. That was really my experience. Was the expectation was that it would be a drop-in, seamless, frictionless replacement for the previous renderer, and I'm not sure that was possible. I think we could get pretty close. There were some very real challenges too with legacy compatibility. One of which I hadn't even thought of when I started working with these guys was because I was just thinking about Direct2D, I was just thinking about performance, and they said, we need to have Direct2D host a child window that is running the old renderer. And then that child window may in turn have a child window that's running OpenGL. So you had this sort of unholy turducken of Direct2D, which wanted the window set up a certain way so that transparency would work nicely and it would perform with specific window flags. If you set the window up that way, it breaks GDI and it breaks the software renderer. So all of a sudden the child window wouldn't show up. And then, so you had that working, but then the OpenGL window wouldn't show up on top of that. And I finally realized that there was like one window flag we're using where the OpenGL window was hiding behind the software, the plugin window, instead of being in front of it in the Z order. None of this stuff is documented about how it works together, or there's anything. None of this stuff is documented to work together or in any way. And it ended up being kind of archaeological, going back and reading about GDI and stuff like that. You're talking about articles that were in, this is all Windows 95 or earlier, like APIs and stuff like that for Windows. And you go back to that, and those articles are gone. I'm looking through Web Archive and stuff like that to read the MSDN blog posts and things like that. It ended up being kind of archaeological, almost, like getting all this stuff running. So the legacy compatibility was a big issue.
Yeah.
And I think changing the component, yeah, I think maybe extending it is something that may happen. That's something which actually we did get that with some of this stuff. Like right now, you can do GPU accelerated effects with images. You couldn't do that before, and that kind of thing. Hopefully that answered your question.
Yeah, it does. It actually brought me to another question, which was
Mhm.
relating to web views versus native C++
Mhm.
rendering. Um, so in my limited research, uh, my understanding is that you will never using web, even if you're using WebGL, you're not going to get the type of performance that you're going to get from.
I'd say that's any type of cross-platform layer, including JUCE. You're going through a translation, and that's gonna impede performance. I think that's always. I think it's compromises, right? It's everything is trade-offs in engineering is what I've found.
Mhm.
I think you can get I haven't worked much with web GPU, but I understand you can get good performance with it. There's a project running in Rust right now called Velo. There's a researcher at Google who's doing some really cutting edge research. It's really cool, and it's all GPU. All the render running entirely in the GPU for Rust rendering,
Mhm.
and that's all through WebGPU because they want it to be cross-platform and they want to just write their shaders once. But I think even if you read their repository, you read their discussions and that kind of thing, there's a reluctant admission that yeah, we probably will have to have a native interface. We probably can't get everything through WebGPU because WebGPU doesn't have the feature set we need.
Mhm.
And uh, it's always a trade-off.
Mhm.
For example, if you want to do this if like say you want to write cross-platform image effects or cross-platform audio rendering, right? It'd be nice to just write that shader once. But on Windows, you've got the high-level shader language. You've got that right, and HLSL, whatever that's called. You've got OpenGL has its own shader language. Metal has its own shader language, and there's not really there's no C++ for shaders unless you just write them once across everything.
Doesn't look like we have any other questions, so feel free to continue
Yes, I'm
on.
crushing it. All right. Okay. Let's see. So the next section of my talk is kind of more for fun, and we're going to talk about Mescal, which is a new module that I'm putting together. And one of the things I'm trying to gauge is the level of community interest in this, but it's basically bonus direct 2D features that didn't make it into the JUCE library. They weren't really a good fit, but there were a bunch of direct 2D features that I thought were fun and that it'd be nice if people had access to them. It'd be nice if I had access to them. So this is a library that builds on top of JUCE 8 that gives you some more fun things. And as tradition dictates, any JUCE related project has to have an acronym that's has your name in it, like JUCE itself, or there's been everyone else that comes up. And so that's my silly forced acronym name for the module. Plus, I just like Mescal. So let me see here. I'm not screen sharing, right? So let me get my screen share switched over. And this also speaks to the problem that we have is that we've just sort of been living in the box. That I find that we aren't necessarily used to being able to do new things. For example, a lot of JUCE developers that I talk to have never heard of a mesh gradient. I hadn't either before all this. Is that coming through?
Yep, all good.
Oh, and the screen sizing's wrong. You can see down there it says direct 2D bonus features for JUCE 8. But if hopefully it's what's coming through in the screen share, it might be kind of blocky. The video compression tends to play a number on this kind of thing. But hopefully you can see the colors cycling in a sort of two-dimensional way. You can see them moving left to right, but they're also moving up and down. And that's a mesh gradient. Normally the gradients, the JUCE supports linear gradients and radial gradients. So a linear gradient will just go along a line from point A to point B. A radial gradient comes out from a center radius and moves out in a circular fashion. This is a grid of vertices where each vertex can be a different color. And it allows for these sort of elaborate kind of, trippy background sort of abstract patterns, or a lot of things actually. Let me give a more concrete example. Okay, so here, this is a mesh gradient made with a single patch. A patch is this kind of shape. It's got four corners, four vertices at the corners, and each side is a Bezier curve. And then there's these interior control points. This is a little harder to see maybe, but this is kind of showing how the colors are distributed. Let me change the color of that vertex so we can make it a little clearer. This is changing kind of how the colors are distributed across. This doesn't always come through visually in the most obvious way, but it changes the kind of the mixing of the colors within there. So all these here, right, we can change this. We can, if you start messing with it, you can make a sort of round shape. And so there's a lot of, it's very flexible, the things you can do. So you can imagine it doesn't have to be a square. It could be a blob. It could be a circle. It could be an ellipse. There's a lot of things you could do with it. Mesh gradients can be formed out of multiple patches. So I'm going to add some more patches here. I'll add that there. And now you can see that we've got you can see that we've got a 3x3 grid, each with its own control points for each patch. I can change this color here now, and that'll change all the colors for all the surrounding patches because they're all linked together. They don't have to be linked. The patches can be discrete as well. So you can get these really interesting, elaborate patterns that come across here. So then you can pull this point around. You can change how the colors are distributed. It's a design element that I feel like I see a lot online now. It's just as backgrounds and things like that. And it's a new feature that you couldn't do with JUCE, and now with this new module, you can do that, at least on top of Direct2D. So another one we've got is one of the things you can do with these mesh gradients is you can bend and torture them and get a conic gradient if you split them up properly. So this is a mesh gradient that's had its math set up just so that the patches, there's a patch that's going right here. You see each of these stopping points? So this is a conic gradient, and this is a mesh gradient that's been bent into a particular shape. And each of these, the patches that I was showing before, that's each of these colors. You can see here, I don't know if, again, this is coming through with the video encoding, but in the screen share, but those are moving a little bit. Let's try, let's say a different color. So that's the HSV color wheel. And you can see now. So this is, again, like you can imagine, what could you do with this? You could do like a radial slider, like some type of radio graphics display. But hopefully what's coming through is that the colors are moving in a sort of a path around the center here, which again, you can't do with any of these gradients in this here. You can go and you can set the size, that sort of thing. So that's another new feature. Direct2D also has a lot of built-in image processing effects. And again, this is all about getting things caught up from, like your iPhone, your Instagram can do image filters and stuff like that, right? You can, you can make things black and white or sepia toned or posterize them and stuff like that. But that's all running on the GPU on the phone. So really some of this is just catching us up to the state of the art or to what everything else can do. For example, here's a demo of a real-time effect running in a shader in the GPU. And there's just a simple slider here to show the amount of blur. Direct2D has a whole bunch of different effects that are all built in. You can do more complex graphs. The nice thing about the effects is you can chain them up together. For example, this is my attempt to build a sort of three-dimensional button. And I think what people have traditionally done is they have taken, they've gone to Photoshop, they've gone to Figma or whatever, and they've generated all the different states of their controls as bitmap, have those as a great big bitmap atlas, and they pluck out the one bit that they need to draw the slider at a particular position. And one of the things I'd like to be able to do is do that procedurally. I'd like to be able to draw the control at a particular position, have it be nicely shadowed and shaded and filled in. And so this is my attempt on the left at a 3D button that's been pushed down. And on the right here, this is the effect graph that it took to do that. These effect graphs work a lot like audio plugin graphs, where you can feed an image, you can feed a plugin into another plugin. They're essentially just plugins. And so, for example, here, I've taken this rounded rectangle, filled in with a gradient. That's just a standard JUCE API call, nothing special there. I've taken the shadow, I've transformed the shadow, and I'm compositing that with the original image. And now you get a nice kind of drop shadow underneath there. So now that's already looking more three-dimensional. Direct3D has an embossing effect. So I've taken a different shape, a different rounded rectangle, a little bit smaller, fed it through the embossing to get that pushed in, kind of, pressed into the screen look. I'm using a chroma key effect to snip off this gray background that's around the outside. And ultimately, all that's getting blended together to give me that kind of 3D looking button there. And the code for this is pretty simple. You can just create these objects. The objects have properties, and you can just stream them together. You just say, feed this one as an input to the next, and it's the actual code ends up being very compact. And let's see, if we go in here, each of these effects has properties, which aren't showing up. Okay, cool. We're not going to do that part of the demo. The demo of Ghost Strike again. Each of these has a set of properties that you can pull up. You can set the shadow color, you can set the affine transform, and there's a straightforward. And what the new module is offering is the ability to, yeah, there we are. Obviously one or two bugs to fix there. What the new module is offering is the ability to do all that in a very sort of JUCE-friendly way. So you configure the gradients with the JUCE color object, with JUCE rectangles and that kind of thing. So it all looks very familiar, and it all builds nicely on top of that. So the snag with this is, of course, all that only runs on Windows. It's and that's the question I think you were getting at earlier, Josh, which is and that's the question I always get as soon as I show people this module. It's like, well, okay, that's a really good point. I'm a JUCE programmer. I want to write cross-platform code. So how do I do that? And that's something I've given a lot of thought to. In fact, I guess ultimately what I've concluded, and this is kind of getting us, we're just going to jump to the next portion of the talk here, is that Direct2D is really just a stepping stone. Is out of date. Direct2D is Windows 8 era technology. So it's 10 years out of date. So the irony is we have gone from Windows 95 era rendering to Windows 8 era rendering, meaning we're just 10 years behind. That's an improvement. And you can see there's just sort of a brief history of what we've done. GDI that we're using for Windows really dates back to Windows 1.0, which is from the 80s. And so we're easily 30 years out of date there. We talked about core graphics card, we'll skip that. And Josh, you were asking about what's the equivalent of Direct2D on the Mac? And you got to think about Linux as well. And I guess ultimately what I've concluded is, even if it was there, I wouldn't want to use it. What I'd like to do, what I hope to do, is to skip all that and go as low level as you can. I thought the point you raised earlier about web GPU was really good, because ultimately, if you want the best performance, if you want to build that crazy complex UI, you need to go down to the hardware level. You need to skip any type of translation layer. And so I'd like to move everything into the GPU. That would be my dream. It was to take all this, build a low-level graphics context that uses all of the modern GPU features, that catches us up from the last 10 years of graphics technology, offloads the CPU, unclogs the message thread, uses all these new features, and really takes it to the next level. That's my dream. And I've spent a fair amount of time thinking about this. This is everything a JUCE low-level graphics context can do. It's maybe a little too small on the screen share, but really it just does like 5 categories of things. That's not that many function calls if you look at it. There's 5 clipping operations you can do, 2 transform operations. There's 10, 12 drawing and filling operations. You got a couple of brush things you can do. So if you can do all that, you can build a better renderer. And to do that, you're going to have to get into shaders. And that's the thing I've really been learning about in the last few months. And again, I'm not an expert at this stuff. I'm still a student. I'm learning. I'm probably going to say something inaccurate. Feel free to correct me. But what I have learned is that shaders are really just little functions that run on the GPU. And I'm not sure what everyone's level of expertise is with this stuff. Someone probably out there knows more than I do, and I'm probably going to say something wrong, and feel free to message me on Discord or whatever. But fundamentally, what it comes down to is, if you're used to writing CPU code, right? If you wanted to process a bitmap, you'd have one, for x equals 0 to the width, for y equals 0 to the height process, and then eventually you're done. And that would all run in a single thread. Maybe if you work really hard, you'd split it into a couple of threads into a thread pool, and they'd all come back together at the end. With the GPU shader, you just have to get used to the idea that you have thousands of cores. You're running thousands of threads at the same time. Maybe they're sequential and stuff like that, but you have to get the idea that you're basically processing, you're going to bring a function that's just going to process 1 pixel, and it's all being divided, and it's all happening at the same time. And it's a really fundamental shift to really get your head around. It's really tough. Shaders, there's different types of shaders. There's vertex shaders that can basically where you pass that mesh. That's what Direct2D does. There's a vertex shader for Direct2D that's going to accept that mesh from Direct2D. The fragment shader colors in the triangles. Compute shaders are what you've probably heard, that's what you use to mine cryptocurrency and to for all those effect images. Those are random compute shaders that I showed earlier. But there's new types of shaders. There's an object shader, sometimes called an amplification shader, that just can take generic objects and create mesh shaders. But the one that I'm really excited about is the idea of a mesh shader, because a mesh shader can create geometry. The mesh shader basically replaces the vertex shader and lets you create the geometry, and that opens up all kinds of possibilities. This is an illustration of how shaders are organized. They come in either a 1D, 2D, or 3D grid. They're groups that make up a grid together. And so a lot of the thinking you have to do with shaders is figuring out, how am I going to organize this grid? How am I going to divide things up? And again, it's a huge, if you're used to CPU-based processing, it's a huge change in your thinking. So a big part of it is figuring out how I'm going to organize it. That's just to dig into it a little more. Say I wanted to draw a rectangle. The software rectangle, I would just be sitting there going through the loop, rasterizing it, the double for loop. I'd be filling in the pixels, trying to do some anti-aliasing. With Direct2D, I'm going to have to take that rectangle and I'm going to create 4 vertices that make up 2 triangles, like that illustration on the right. I'm going to transform that rectangle, whatever transforms pass through the renderer. I'm going to pass that mesh to the vertex shader. It's a very simple mesh of 2 triangles, but the vertex shader will take that, transform it into the coordinate space of the GPU, and ultimately it gets painted by the fragment shader. What I'd like to happen is I'd like to not generate that geometry on the CPU. What I want to do is I want to generate the geometry on the GPU. I want to have as little overhead on the CPU side as possible, which means I just want to pass a command to say, draw a rectangle to the GPU object shader. The object shader would then, there'd be, so 1 thread per one of those shapes that I want to draw. It then spawns off 4 mesh threads. So there's a grid of, this is hard to explain, but there's a grid that then spawns multiple grids. And each of those mesh shaders generates the vertices and the triangles, which then gets colored by the shader. In other words, the whole computational load of all of that stuff that has to happen. And if that's just 1 rectangle, that's no big deal. But if it's tens of thousands of rectangles, that starts to get interesting. So that being said, what we got here is this is a prototype metal renderer running on the Mac, doing exactly what I was describing just now. And so this is what I was referring to earlier, Josh. I don't know what the equivalent of is on Direct2D on the Mac. Not sure there is one, and I sort of don't care because I want to go past that. I want to just jump over it, and I want to go right to metal. I want to basically, my goal is, you can see here, there's a lot of it's running already. This is just an engineering demo. It's just a prototype. It's not the real thing. There's a ton of work to be done on it. But over here, we're filling rectangles. We're filling a rectangle list. It's drawing rectangles. It's drawing ellipses and circles. There's some paths being filled and stroked here, and it's doing text. The image rendering isn't working. I don't know why yet. Right now, it's about 4 to 5 times as fast as the core graphics renderer, and I think it could actually be considerably faster. And the thing that I think is really exciting about this as much as anything is not only do you get better graphics performance this way, not only are you offloading the message thread, not only are you freeing up CPU time for your signal processing and stuff like that, this lets you access the GPU. This lets you as a developer start thinking about, you can write your own shaders. You can access the absolutely massive amount of computing power that's inside the GPU. You can start writing your own image effects and stuff like that. It opens up a whole new world of computing power that you haven't had access up until now as a JUCE user. And that's what really excites me. So this is very much early days. I've only had this running recently, and it needs a lot of work to really be a full-fledged usable thing. Taking all the lessons we learned from doing Direct2D and realizing, what people actually need and how this should actually work. But yeah, that's this is where I think it should go. And all of these ideas could be ported back to DirectX 12. They could be ported back to Vulkan. In other words, you could have this architecture on every platform across everything. And it's something I'm actually pretty excited about. I've been working on it, and the more I've looked at it, the more excited I get, the better I think it can be. I think that's about all I had. That's my contact info, and Josh, I'd be happy to take questions now.
Yeah, so I have another question.
Mhm.
So in terms of your vision of how the metal renderer and then porting
Mhm.
it back to a Windows compatible equivalent,
Mhm.
how, in your vision, how would that manifest itself in terms of what the developer is actually coding in? Because I've heard that actually drawing using I don't know what the proper terminology is, but drawing in metal is actually quite difficult or has a steep learning curve. So
Um,
would that be a C++ abstraction, or how would that
oh,
work?
oh, so you would be hidden from it. It's okay. So that's a really good question. Let's look at the code. Okay, yeah, it's a low level graphics context implementation. So that app I was just showing you, all that drawing that was happening. Let's pull that up. That was all just stock juice code. Everything that's happening there.
Okay, interesting.
So that's the point of all of this. It's the same thing with Direct2D, right? Which is, where are we? Here's the code. There's a bunch of commented out code that no one wants to see, right?
Mhm.
So this is just my paint handler. This is a class called Painter that's just taking a juice graphics object and
Mhm.
and an area, and it's just got a little bit of timing information there. But all I'm doing, this is doing the metal drawing here, right? So this is like so what I'm drawing, a red rectangle. Here's an orange rectangle. Here's a rectangle list in yellow, right here. And down here, what am I doing? I'm drawing an outline of a rectangle, and I'm kind of oscillating the thickness based on the animation time. And here we're filling an ellipse, and here I'm drawing an ellipse in indigo. And then down here, I'm drawing text. The quick brown fox jumps over the lazy dog, right? So this is all just stock juice graphics calls,
Got it. So you're
right?
just suggesting that they just change what happens
Well, that's how
below.
Direct2D works, right? Is if we look at the graphics stack here, and then how do I do this? Right? It's just so you have a no, that's not the right shape. Let's do one of these. Okay. Okay, there we go. So if this is your component, right? And then your paint handler, you're talking to the Juice graphics class, right? Everybody's used that, who's used Juice, right? Below the Juice graphics class is the low level graphics context. And this is going to be different depending on each platform, the LLGC, right? This is going to be core graphics, maybe. It's going to be Direct2D, it might be GDI, it might be something like that, right? This would just be a metal level graphics context.
Right.
So your layer up here at the top, unchanged.
Right.
Now, with the caveat that the stuff I talked about earlier, that with the difficulties with the object model and the fact that a GPU-based renderer doesn't necessarily fit into the existing model, and then we've got to tweak that because of that whole circle ellipse thing. But that would be true of any GPU-based renderer. But fundamentally, if you just want to draw text, if you just want to fill a rectangle, that kind of thing, fill in the background as orange, it's exactly the same.
Right. 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 So you're just suggesting to use the GPU no matter what you're drawing. Like,
Yeah, what I'm suggesting is replacing this layer here. Is the low level graphics context down there. That's that. I feel like I may not have explained that very well. I guess if you say stroke a path, what normally happens, right? That generates the CPU starts rasterizing that, and I guess yeah, I'm suggesting that all of that could be moved into the GPU with no intervention on the part of the CPU.
right.
Without all those, like, we were talking earlier about web GPU and the performance issues and that kind of thing, because of the necessary translation. I'm saying essentially we move all the translation into the GPU and all the mesh generation and all the rasterization into the GPU. Essentially offload it completely and free the GPU app. I was originally contemplating some type of threading scheme where with Direct2D, where you build up a bunch of threads, you build up a bunch of commands in your paint handler, and then that gets pushed off to a thread. Like, for instance, that's how Firefox works. But let's not even do that. Let's just dump it all. Just get rid of it all. Don't do any rendering on the CPU. It's
Mhm.
it's the wrong tool for the job. Move
You were
all the
saying
render.
that the problem with that was that one of the requirements was that you have a regular component that could host any other different types of components, like an OpenGL component.
That was an issue with Direct2D. Yeah, yeah.
Right.
Yeah, that's and I think in retrospect, if I had it to do over again, I would have made Direct2D. I would have suggested that it isn't my call, but one other approach we could have taken that might have been better like with OpenGL, there's the OpenGL attachment in JUCE that you put in your component. Like you instantiate this one thing and say, and then you just get OpenGL rendering. So it's opt-in to OpenGL. Direct2D could have worked that way too. Direct2D could have been an opt-in attachment that you put in your class, and then everything got faster. But
Mm.
you know, the software render, maybe that should have been the default. It's hard to say. There's an argument to be made that that would have been better, and I think that might be the approach. That's what I've got now with that new app, is that the metal is an attachment that you put in your component, and then it actually creates a child window inside there, and it's actually rendering everything in metal inside that child window, which is seamless to you. You don't notice anything. That all happens under the hood.
Mhm. Got it. So you could opt in or opt out per
Yeah,
component.
by just creating a metal attachment in your as part of your component, you should have a metal attachment member variable in your class, and that's literally all you'd have to do. And so yeah, so ultimately, the goal is as much as possible, given the limitations of the object module, to have it so that you just drop this in, and all the rendering moves to the GPU. And we're not quite there yet, but that's the ultimate final form of the whole thing.
Yeah, love that.
Oh, we'll see.
Um, so there was a comment from Revolt DSP that says, I render out my shaders and textures on Blender, then skin the
Hmm.
plugin with images. GPU render for C++ would open
Hmm.
so many possibilities.
Rock and roll.
Oh, we do have one more question, Matt, from Revolt DSP, asking where they can find out more about Metal, the Metal API.
There's a really good website called metalbyexample.com that has really good tutorials, and I really rely. He does, I think, a better job than the Apple documentation is a bit of a mix of some of the important information is actually buried in the sample apps, not the documentation itself. And the Metal by Example guy does a really good job. It's been around and he just did a sort of retrospective on from scratch about how do you write a Metal app from beginning to end. Metal is pretty user friendly, I found. It's if we're it's like there's a oh, I'm gonna hijack your meeting here for a second, Josh. There's a good example here on just called Hello Triangle. That's probably the best. That's where I started. And where's my Xcode? There we go. And so they've got a really nice example. Like here's all the shaders, for instance. Just in the, oh no, that's not the shaders. That's the shaders. So for example, here's the vertex shader, and you can see that that's just a really simple example here. And you know, here's the fragment shader. They've got a renderer set up that creates the shaders, instantiates them, shows you how to talk to them, show you how to pass parameters to them, and it just gives you a nice kind of simple. It's a nice simple example. It's taking forever to come up. Go ahead and message me on Discord if you want to talk more. Josh, is there going to be some place we can post, links and that kind of thing afterwards? Or are you just going to put up people's contact info at the end?
Yeah, I'll put people's contact info within the video description.
Perfect.
Uh, and
Yeah,
then, yeah, feel free, happy to put it also in the video, in the announcement on Discord,
great.
and
Yeah.
meet up.
Yeah,
The
but hit me up on Discord. We can talk about it more. There's yeah, metal's really cool, and
Yeah,
yeah, stuff's a lot of fun.
I love that. I think that's everything that we have for everybody that we have for questions. Matt, thanks so much.
Mhm.
That's really
Okay,
awesome.
I think I went a little over. Sorry about that.
Oh, that's all right.
Sorry for the chaos. It was a bit of a last minute faff. Thank you very much. Thank you for having me.
Thank you so much, Matt.